Good evening, everyone. Welcome to another tutorial of Applied Thermodynamics course. I am Tharanga Sutia. We'll wait for a couple of minutes for others to join, and in the meanwhile, I'll share my screen. I hope you can see my screen. So we'll wait for 1 or 2 minutes. Okay. So let us start today's class. In this class, we will be dealing sums that are related to Brayton cycle. Remember when we have started our classes for power cycles, there were two types of power cycles: vapor power cycle and gas power cycle. Okay. It only depends on the working fluid. Here working fluid is vapor, and here our working fluid is gas. Okay, so Brayton cycle is an example of a gas power cycle. Okay, and this example is a Rankine cycle, which we have already studied. Clear? So today we will be dealing sums that are related to Brayton cycle. Okay, so before going to do the sums, let us come across what is a Brayton cycle. Okay. Brayton cycle, it consists of 4 processes. Okay, 2 reversible adiabatic processes, and 2 constant pressure, heat, addition or rejection processes. Okay, so in order to more clearly understand it, let us look at the TS diagram. Okay, one, two, three, 4. Okay, so the processes are 1 to 2 reversible adiabatic compression. Okay, 2 to 3 constant pressure, heat, addition, 3 to 4 reversible adiabatic expansion, and 4 to 1 constant pressure heat rejection. So these are the 4 processes which we have to deal in with. If so this will be a constant pressure heat addition Q1, Q2 is the constant pressure heat rejection, WC is the adiabatic work of compression, and WE is the adiabatic work of expansion. Okay, so these are the different processes. Now let us look at the formula for efficiency of a Brayton cycle. Okay, so efficiency of a Brayton I know that in the theory classes the assumptions of the ideal Brayton cycle or whatever it is, this has been taught very nicely, so I'll quickly deal with how the efficiency formula came into picture. Okay, eta Brayton, as we know that whatever may be the cycle, the efficiency is basically output divided by input. So what is the output? That is basically work net divided by what is your input, Q1. Okay, and W net, we can write this W net as WE minus WC divided by Q1. Okay, so better let me write this one as heat input okay. This I can write this one as Q1 minus Q2 divided by Q1. So this can also be written as 1 minus Q2 divided by Q1. Okay, now remember your Q2 is a constant pressure heat addition, so Q2 I can write per unit mass Q2. If I want to write this, I can write this as Cp, or let me write it as M. Okay, M Cp T4 minus T1, and Q1 I can write as M Cp T3 minus T2. Why? Because these processes are constant pressure processes. Okay, so from here eta Brayton will become 1 minus M Cp T4 minus T1 divided by M Cp T3 minus T2. Okay, so this can be written as 1 minus T4 minus T1 divided by T3 minus T2. Okay, now what I can write, T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. Yes or no? Because this is a reversible adiabatic process. Okay, so from here I can write T2 is equal to T1 into P2 by P1 to the power gamma minus 1 divided by gamma. Now let me name this as Rp, then this will be gamma minus 1 divided by gamma, where Rp is equal to P2 divided by P1. Okay, fine. Similarly, for the process, this one T3 divided by T4 can also be written as P3 divided by P4 to the power gamma minus 1 divided by gamma. Now remember, this process 2 to 3 is constant pressure process, so P2 is equals to P3 and P1 is equals to P4. So what I can write, T3 divided by T4 is nothing but P2 divided by P1 to the power gamma minus 1 divided by gamma, and this can be written as T3 divided by T4 is equal to Rp to the power gamma minus 1 divided by gamma. Okay, clear? So that means what? T3 can be written as T4 into Rp to the power gamma minus 1 divided by gamma. Okay, now eta Brayton can be written as 1 minus T4 minus T1 divided by T3 minus T2. Now this one 1 minus T4 and T1 I will put as it is, and this T3 I can write as T4 times Rp to the power gamma minus 1 divided by gamma. Yes or no? And this one also I can write T2 is equals to T1 into Rp to the power gamma minus 1 divided by gamma. Okay, so now what I am getting here as Rp to the power gamma minus 1 divided by gamma is common, so from here I will get this one as T4 minus T1. Okay, so finally what we get is that even if we know only the pressure ratio, then also we can calculate the efficiency of a Brayton cycle. Fine. So this is when we know the pressure ratio. Okay, so let us come back to question number 1 then. Calculate the thermal efficiency of an ideal Brayton cycle if the pressure ratio is 6. Okay, calculate the, so why I am writing the question, I'm sorry. So solution of 1 will be what? Given P2 by P1 that is equal to Rp is given as 6. Okay, so we have to calculate the efficiency. Now eta Brayton, that will be simple, 1 minus 1 by Rp to the power gamma minus 1 divided by gamma. Now here gamma value is not given. Okay, now if it is an ideal cycle, so AR is used, and in that case gamma is equals to 1.4 for using all the air standard assumptions. Now just you have to put all these values, 1 minus 1 by 6 to the power 0.4 divided by 1.4. Okay, so this one you'll get as 40.06%. Clear? So first of all we have derived an expression for calculating the efficiency of a Brayton cycle if we only know the pressure ratio, and from that only we have calculated the efficiency, since in our question pressure ratio is already provided to us. Okay, clear? Okay, so let us go to the next question then. Helium is used as a working fluid in an ideal Brayton cycle. The gas enters the compressor at 27 degrees Celsius in 20 bar pressure. The gas is heated to 1000 degrees Celsius 60 bar pressure before entering the turbine. The cooler returns the hot turbine exhaust to the temperature of the compressor inlet. Calculate the work done by the turbine, work done by the compressor, heat added, heat released, and efficiency. Cp and gamma value is given. So in the previous question, no any working fluid was given, and we assume that it's an ideal, perfectly ideal Brayton cycle, and so air is mostly used. So we have used the gamma value for air. Now here we will be using the gamma or Cp values for helium, because helium is the working fluid. Okay, and since it is also an ideal gas, so rest all assumptions will remain the same. Only the working fluid will change from air to helium. Okay, so before going to solve this, let us see the TS diagram once again. Okay, so what are the things that are given to us now? Let me write these also. Okay, so now given the gas enters the compressor, so 1 to 2 is the compressor process, so T1 is given to you as 27 degrees Celsius, so this one 273 plus this one, I can write this one as 300 Kelvin, and P1 is given to you as 21. Okay, next, the gas is heated to 1000 degrees Celsius and 60 bar pressure before entering the turbine. Now turbine process is 3 to 4, so before entering the turbine, that means it is the point 3 telling us. Okay, so T3 is 100 degrees Celsius, which I can write as 1273 Kelvin. Okay, and P4, sorry, and P3 is equal to what? 60 bar. Okay, now the cooler returns the hot turbine exhaust. What is the cooler? Cooler is the process 4 to 1, so that means the cooler cools the hot turbine exhaust to the compressor inlet. That means it is a complete repetition cycle. Okay, so that means T1 is back again to 300 Kelvin. So now we all know that if P1 is given, then P4 is also given, and if P3 is given, then P2 is also given. Okay, and Cp is given to us as 5.1926 kilojoule per kg Kelvin, and gamma is given to you as 1.66. Okay, so from here we have to calculate the work done by the turbine. So our goal is to calculate temperature at all the points. Okay, now if you calculate the temperature at all the points, then you just have to calculate the enthalpy, and enthalpy for an ideal gas is Cp into delta T. Okay, clear? Okay, so now let us calculate the temperature at the point 2. Okay, for the process 1 to 2, T2 divided by T1 is equal to P2 divided by P1 to the power gamma minus 1 divided by gamma, and from here T2 is equals to T1 into P2 by P1 to the power gamma minus 1 divided by gamma. So T2 will be equal to, T1 is what? 300. Okay, P2 is 60, and this is 20 to the power 1.66 minus 1 divided by 1.66. Okay, so from here T2 is equal to what? 464.32 Kelvin. Okay, so this is T2. So we know T1, we know T2, we know T3. Now we want to know T4. Okay, so for the process 3 to 4, T3 divided by T4 is equal to P3 divided by P4 to the power gamma minus 1 divided by gamma. So from here T4 is equal to T3 divided by P3 by P4 to the power gamma minus 1 divided by gamma. So what is T3? 1273. What is P3? 60. And what is P4? 20. 0.66 divided by 1.66. Okay. So from here T4 is equal to what? 822.48 Kelvin. Okay, so we have T1, we have T2, we have T3, and we have T4. Now work done by the turbine. Work done by the turbine. Okay, so that means WE. So turbine process is 3 to 4. So WE is nothing but H3 minus H4. So this will be CP T3 minus T4. So what is your CP? 5.1926. T3 1273 and T4 is 822.48. So this one kilojoule per kg. Okay. So this is 2339.37 kilojoule per kg. Okay. Next is what? Work done, not actually work required. Okay, so this will be work required by the compressor. Okay, WC, that will be equal to what? H2 minus H1 required. So WC, that will be H2 minus H1, that will be CP T2 minus T1. Okay, 5.1926 464 32 minus 300 kilojoule per kg. Okay, so WC eight 3.25 kilojoule per kg. This is the work required by the compressor. Okay, next, heat added. Okay, that is Q1, that will be equal to CP T3 minus T2. Okay, 5.1926. What is T3? 1273 and T2 464.32 kilojoule per kg. Okay, 5.1926 into 1273 minus 464.32. This will be 4199.15 kilojoule per kg. And next is heat rejected, that is Q2, and that will be equal to CP into T4 minus T1, 5.1926 into what is T4 822.48 and what is T1 300 kilojoule per kg. Okay, two seven 13.029 kilojoule per kg. Okay, and next is your efficiency. Efficiency of the cycle eta W net divided by Q1, that is Q1 minus Q2 divided by Q1. What is Q1? 4199.15, Q2 2713.029 divided by 4199.15. Okay, 4199.15 minus 2713.029 divided by 4199.15. So it is 35.39%. Alternatively, we also can calculate how, because we know the pressure ratio RP, that is P2 by P1 is equal to what? 60 divided by 20, that is equal to 3. So therefore eta is equal to 1 minus 1 by Rp to the power gamma minus 1 divided by gamma, that is 1 minus 1 by 3 to the power 0.66 divided by 1.66. Okay, this is also 35.389%, that means almost equal to 35.39%. Okay, so however you do, you will get the same efficiency, but here it was a rather more tedious task because you have to also calculate the other parameters like the work done by the turbine, the work required by the compressor, and so on and so forth. Okay, so and from there also we can calculate the efficiency, but if you know the pressure ratio, you can directly calculate the efficiency just like in the previous questions. Okay. Okay, so let us move to the next question then. In a gas turbine plant working on Brayton cycle, hot combustion gases from the combustion chamber enter into the gas turbine at 1450 Kelvin and 20 bar and exits at 1 bar. The isentropic efficiency of the gas turbine is 0.90. Calculate the work developed by the turbine per kg of the gas flow. Okay, so before going to solve, let us once again draw the TS diagram. Now this is a bit different from the previous questions, because in the previous questions our point 4 was exactly at the point 4s. Okay, but now what is happening is that our 3 to 4 process is not a reversible adiabatic process. Okay, so before that let us write the given conditions given. T3 is equal to 1450 Kelvin. P3 is equal to 20 bar and P4 is equal to 1 bar. Okay, and eta isentropic is equals to 0.90 for the turbine. Okay, eta turbine is equals to 0.90. Okay, so in this question, the turbine process, turbine expansion process 3 to 4 is not reversible adiabatic process. Okay, so that is only the difference. So if this is, so then in that case how we will do this? Okay, so one thing is given to us, that eta isentropic. So isentropic efficiency this is nothing but actual work done divided by work done if actual work done in the process divided by work done if the process would have been isentropic. Okay, so if it would have been isentropic, it would have been expanded to a larger distance. Okay, but since this is not expanding to a larger distance, so we have to now calculate the expansion process. Okay, so now if the process would have been isentropic, now for the reversible adiabatic process 3 to 4s, not 4, okay, 3 to 4s, what we can write, T3 by T4s is equals to P3 by P4s to the power gamma minus 1 divided by gamma. Now these 4s and 4 are in the same pressure line, so that means they are a constant. That means the P4 is equals to P4s, P4 is equals to P4s. Okay, so this means T4s is equals to T3 divided by P3 by P4 to the power gamma minus 1 divided by gamma. What is T3? 1450. What is P3? 20 by 1. And what is gamma? Cp and Cv value are given. Okay, so gamma is equals to Cp divided by Cv. 1 divided by 0.769. 1.3. 1.3. Okay, so it will be 0.3 divided by 1.3. Okay, so from here T4s is equals to what? 1450 divided by 20 to the power 0.3. So it is 726.323 Kelvin. Okay, now eta isentropic. Again I am writing once again actual work done in the process divided by work done if the process would have been isentropic. Okay, now for the turbine isentropic expansion for the turbine, this would be what? If the process, what is the actual process? Actual process is 3 to 4. So actual work done in this process is H3 minus H4. Correct, no? For the turbine. And if it would have been isentropic, H3 to H4s. Okay. So Again, this one is what we have to calculate. This is what we have to calculate. That is the actual work done by the turbine. And this one is what I can write this one as Cp into T3 minus T4s. We have Cp, we have T3, we have T4s. So from here we can write H3 minus H4 is nothing but eta turbine into Cp into T3 minus T4s. Okay, so that means work done by turbine eta T is 0.90, Cp is 1.00, T3 is what, 1450, and T4s is what, 726.323. This will be kilojoule per kg. Okay. .651.309 kilojoule per kg. Okay, is it done? So that means what, this gives also to us an indication, and from here also what we can do, from here we can also calculate T4. How we can calculate T4? Eta T will be equal to what? H3 minus H4 divided by H3 minus H4s. Okay, so eta T will be what now? Cp into T3 minus T4 divided by Cp into T3 minus T4s. We'll cut this Cp. We know T3, we know we have to calculate T4, we know T4s, and we know T3, and we know eta T. So from here T4 can also be calculated. Okay, so the actual temperature of expansion can also be calculated from this. Okay, so the only difference of this question with the previous one, previous two questions we have done is that here the expansion process in the turbine, we don't know about the other processes, but the expansion processes of the turbine is not reversible adiabatic, or we can say that it is not isentropic. Now how will we know that the expansion process is not completely isentropic? How will we know that expansion or compression process is not isentropic when the isentropic efficiency of compressor or turbine is provided? This means that compression or expansion process is not isentropic. Okay, so here nothing was said about the compressor, so we have written it as completely reversibles adiabatic, that is isentropic. Okay, is it clear? Okay, so let us move to the next question then. In a gas turbine power plant, if the maximum temperature in the cycle is 1200 Kelvin and the minimum temperature in the cycle is 300 Kelvin, the isentropic efficiency of the compressor and the turbine is 0.8 each, then what will be the value of optimum pressure ratio approximately for maximum work output in the cycle? Okay, so before going to do this, once again we have to derive an expression for optimum pressure ratio. Okay, so how will we do that? So these are the different processes we know. So T max is nothing but T3 and T min is nothing but T1. So we will derive an expression for optimum pressure ratio with respect to these all parameters. Okay. Now what is optimum pressure ratio? It is the pressure ratio corresponding to optimum pressure ratio what is it? It is the pressure ratio corresponding to maximum work output in the cycle. Okay, so that means what? We have to develop an expression for maximum work output. Okay, so we know that eta Brayton is equal to what? 1 minus 1 by rp to the power gamma minus 1 divided by gamma. Okay, and eta Brayton is basically what? W net divided by Q1 is equal to 1 minus 1 by rp to the power gamma minus 1 divided by gamma. Okay, so what is Q1? W net Q1 is what? Cp T3 minus T2 is equal to 1 minus 1 by rp to the power gamma minus 1 divided by gamma. Okay, so from this what I can write this one as W net is equal to Cp into T3 minus T2 into 1 minus 1 by rp to the power gamma minus 1 divided by gamma. Okay, now T3 is the maximum temperature, but T2 I can express in terms of minimum temperature also. How? T2 divided by T1 is equals to P2 divided by P1 to the power gamma minus 1 divided by gamma. So from here T2 is equals to what? T1 into rp to the power gamma minus 1 divided by gamma. Okay, so from here W net is equals to what? Cp into T3 minus T1 into rp to the power gamma minus 1 divided by gamma into 1 minus 1 by rp to the power gamma minus 1 divided by gamma. Okay, fine. Now I'll just multiply it. W net is equals to what? Cp T3 minus T3 divided by rp to the power gamma minus 1 divided by gamma minus T1 into rp to the power gamma minus 1 divided by gamma plus T1. Okay, I have just multiplied these two terms. Now for the same maximum and minimum temperature, that means if these two are constant, W net is nothing but a function of rp. Okay, so what we can write, therefore dW net divided by drp is equals to what? Cp it's a constant, it will remain outside. T3 is a constant, it will remain 0 minus T3 into minus gamma minus 1 divided by gamma into rp to the power minus gamma minus 1 by gamma minus 1. Okay, minus T1 gamma minus 1 by gamma into Rp to the power gamma minus 1 by gamma minus 1, okay, plus 0. Fine. So dW net divided by dRp is equal to what? Cp into minus minus plus, so this T3 into gamma minus 1 by gamma into Rp to the power minus gamma plus 1 minus gamma divided by gamma minus T1 into gamma minus 1 divided by gamma into Rp to the power gamma minus 1 minus gamma divided by gamma, okay. So again dW net divided by dRp is equal to Cp into, I will be taking out gamma minus 1 by gamma also, this will be T3 into Rp to the power 1 minus 2 gamma divided by gamma, and this will be equal to T1 into Rp to the power minus 1 by gamma, okay. So for maximum work output, dW net divided by dRp must be equal to 0. So that means Cp into gamma minus 1 divided by gamma into T3 into Rp to the power 1 minus 2 gamma divided by gamma minus T1 into Rp to the power minus 1 by gamma is equal to 0. Fine. So these two terms will go. So that means basically T3 into Rp to the power 1 minus 2 gamma divided by gamma is equal to T1 into Rp to the power minus 1 by gamma, okay. Now T3 divided by T1 will be equal to Rp to the power minus 1 by gamma minus 1 minus 2 gamma divided by gamma. Clear? So from here T3 by T1 is equals to Rp to the power gamma minus 1 plus 2 gamma. So that means what? T3 by T1 is equal to Rp to the power 2 into gamma minus 1 divided by gamma, okay. So Rp optimum is nothing but T3 by T1 to the power gamma by 2 into gamma minus 1, okay. So this is the case when no isentropic efficiency. This is the case. This is the expression for optimum pressure ratio when compression and expansion processes are isentropic. But what if isentropic efficiency are provided? Now if eta T and eta C are the isentropic efficiencies of turbine and compressor respectively, then what happens? Rp optimum will be nothing, eta C, eta T, T3 by T1 to the power gamma divided by 2 into gamma minus 1, okay. So this is the expression and this is one expression. Now let us see the question what it is given to us, okay. So in a gas turbine plant, maximum temperature, that means T3 is given. Which question is this? Solution to question number 4. Okay. T3 is given to us as 1200 Kelvin. T1 minimum temperature is given to us as 300 Kelvin. Okay, and eta compressor is given to us as what it is telling us that the isentropic efficiency of compression the turbine is about 0.8. Okay, so compressor is equals to 0.8 and turbine is also equal to 0.8. So therefore pressure ratio optimum will be equal to what? 0.8. Let me write the expression once again. Eta C, eta T, T3 by T1 to the power gamma by 2 into gamma minus 1. Okay, 0.8, 0.8, 1200 by 300 to the power. Are they telling us the value of gamma? So it's a gas turbine power plant, so gamma that will be equal to 1.4. Okay, zero 0.4 divided by 2, sorry, 1.4 divided by 2 into 0.4. So this is the optimum pressure ratio is equals to 5.18. Okay, have any doubt? Okay, fine. So let us go to the next question then. A gas turbine operating on a Brayton cycle has two stages of compression with intercooling between the two stages and two turbine stages with reheat between the two stages. The pressure ratio of both the turbine stages and both compressor stages is 5:1. Air enters both the compressor stages at 300 Kelvin. The gas enters both the turbine stages at 1500 Kelvin. Both compressor stages have isentropic efficiencies of 85% and both turbine stages have isentropic efficiencies of 90%. The intake pressure of the engine P1 is 100 kilopascal. Sketch this cycle numbering all the points and draw a TS diagram for it, clearly showing all the processes. Okay, fine. So what is basically happening here? There are two stages of compressions. Okay, so if this is one compression, okay, after that what happens? Intercooler, so it cools down. After that compression, this back again it is cooling down to this original temperature and back again it is getting compressed. Okay, so 2 to 3 it's basically a cooling process, and then 3 to 4 once again it is a compression process. So this is compression 1, this is compression 2. Fine. After that, what happens? This is the combustion chamber. Combustion chamber. Okay. From 4 to 5. Now, once again, it is getting expanded in a turbine. Okay. Now, after it is being expanded to the turbine, once again this undergoes a reheater. Okay. Then again it is getting expanded to turbine 2. Okay. Then from here, this is this cooler. Fine. This is the overall process. So there are two stages of compression, compression 1 to 2, and there are two stages of two stages of compression are 1 to 2 and 3 to 4, and two stages of expansion are 5 to 6 and 7 to 8. Okay. So let us draw the TS diagram also. One to two compression. Okay. Then 2 to 3 there is again cooling. So that means the temperature will be getting dropped to again this original temperature T1. So this is the process 2 to 3. Okay. 3 to 4 again compression. Fine. Then 4 to 5 heat addition. Then 5 to 6 expansion. Again there is a reheating up to this temperature. Okay. And then 7 to 8 this is the TS diagram if you want to see that. Okay. Clear? Now what are the things that are given? P1 is equal to 100 kilopascal. Okay. And air enters both the compressor stage at this one. So T1 is equal to 300 Kelvin and T3 is equals to 300 Kelvin. So both the compressor stages, and gas enters both the turbine stages at 1500 Kelvin. So that means T5 is equal to T7 is equal to 1500 Kelvin. Okay. And then both the compressors have isentropic efficiencies. Okay, so that means these two processes. So even though I have drawn it in a straight line, but you have to remember that the compression processes are not isentropic and the expansion processes are also not isentropic. Okay. And yeah, one more, both the pressure ratio of both the turbine stages and both the compressor stages is 5:1. So that means RP for all the stages are, what I can write this one is P2 by P1 is equals to P4 by P3 is equals to P5 by P6 is equals to P7 by P8 is equals to 5. Okay, so these are the things that are given to us. So from here we have to then calculate the what we have to calculate. We have sketched this, and including we have to specific work at each compressor stage and then determine the specific work, and also we have to calculate the efficiencies. Okay, fine. Now first of all, calculating the outlet temperature of the first and second stage compressor. Okay, for the process 1 to 2, so basically let me draw this one. This is 2s, okay, I can put it this way also, no problem. 1 2 3 4 5 6 7. Okay, so for the process 1 to 2, T2 divided by T1 is equal to P2 divided by P1 to the power gamma minus 1 divided by gamma. Okay, so this P2 divided by P1 is basically equal to 5, so T2 is equals to T1 into P2 by P1 to the power gamma minus 1 divided by gamma. What is T1? 300. What is P2 divided by P1? 5. And 1.353 minus 1 divided by 1.353. Okay, for 56.54 Kelvin. Okay, but this is not the actual temperature exit because the efficiency is given to you. Okay, so for the actual temperature at the outlet of the first compressor, eta compression is what? Isentropic work divided by real work. Okay, so eta compression will be nothing but T2 minus T1 divided by T2 prime minus T1. Okay, so compression isentropic is given to you as this one, so T2 is 456.54 minus 300 divided by T2 prime minus 300. Okay, so T2 prime minus 300 is equal to what? .16, so this one T2 prime is equals to what? 484.16 Kelvin. Okay, so this is the actual temperature exit at the first compressor. Okay. Next is what? For the process 3 to 4, T4 by T3 is equal to P4 by P3 to the power gamma minus 1 divided by gamma. So from here T4 is equal to T3 into P4 by P3 to the power gamma minus 1 divided by gamma. So once again this T3 is this same only. So if you put all these values, T3 is 300 into 5 to the power 1.353 minus 1 divided by 1.353. You will get this as 456.54 Kelvin. Okay. Again, the actual temperature at the outlet of the second compressor. So that will be again eta compression will be equal to isentropic work divided by real work. Okay. T4 minus T3 divided by T4 prime minus T3 now. Okay. So again 0.85, this T4 is what? 456.54 minus T3 is what? 300. T4 prime minus 300. So from here it's just like the previous one. You will get this one as 484.16 Kelvin. Next is what? Calculating outlet temperatures of the first and second stage turbine. Okay. For the process 5 to 6, T5 divided by T6 is equal to P5 divided by P6 to the power gamma minus 1 divided by gamma. And from here so T5 is given to you as 1500 Kelvin. So T6 will be nothing but T5 divided by P5 by P6 to the power gamma minus 1 divided by gamma. T5 is 1500, 5 to the power 1.353 minus 1 divided by 1.353. Okay. So it is 985.66 Kelvin. Now actual temperature, because this is not an isentropic process, so isentropic efficiency is given to you, therefore actual temperature at the outlet of the first turbine. Now eta turbine, this is just the opposite, real work divided by isentropic work. Okay, and turbine, this is what eta turbine, this will be now T5 minus T6 prime divided by T5 minus T6. Okay, and this is given to you as 0.90 is equal to what? 1500 minus T6 prime divided by 1500 minus 985.66. Okay, so from here T6 prime will be equal to what? 0.90 into 1500 minus 985.66. Okay, 1500 minus, so this is 1037.09 Kelvin. 1037.09 Kelvin. Okay. Next again, temperature at the outlet of the second stage turbine. Okay, so T7 divided by T8 is equal to P7 divided by P8 to the power gamma minus 1 divided by gamma, and from here T8 is nothing but T7 divided by P7 by P8 to the power gamma minus 1 by gamma. So T8 is nothing but 1500 divided by 5 to the power 1.353 minus 1 divided by 1.353, which will be equal to 985.66 Kelvin. Okay, and again actual temperature at the outlet of second stage turbine, this will be calculated by using the isentropic efficiency, that is isentropic work by real work, real work by isentropic work, since it is a turbine, I'm sorry. So real work by isentropic work. Okay. So 0.90, that will be equal to T7 minus T8 prime divided by T7 minus T8. So 0.90, that will be T7 1500 minus T8 prime divided by 1500 minus 985.66, and using all these values you will get T8 prime is equals to 1037.09 Kelvin. Okay. Now therefore work required by each compressor, WC1, that is Cp T2 prime minus T1. Okay, so what is the Cp value they are given? 1.10. 1.10. What is T2 prime you have got? 484.16. 484.16 minus 300. Okay, 1.10 into 484.16 minus 300, so that is 202.57 kilojoule per kg. Okay. This will also be equal to compressor work, similar, because the temperatures are also the same. Cp T4 prime minus T3, that is nothing but 1.10 into 484.16 minus 300, which will also be equal to your 202.57 kilojoule per kg. So therefore total work required by compressor is equal to what? WC1 plus WC2, that is what? 2 into 202.57, 405.14 kilojoule per kg. Okay. Similarly, work done by each turbine. Okay, so WT1 is equal to what? Cp T5 minus T6 prime, 1.10. What is T5? 1500 minus T6 prime is 1037.09 kilojoule per kg. 509.509.201 kilojoule per kg. Similarly, WT2 will be nothing but Cp times T7 minus T8 prime, which is also the same values, 1500 minus 1037.09 kilojoule per kg, that is 509.201 kilojoule per kg. So therefore total work done by turbines is equal to what? WT1 plus WT2. Okay, one 1018.402 kilojoule per kg. Okay, next is what? Total heat addition in the cycle. Okay, so that will be equal to what? Heat addition in the combustion chamber and heat addition during reheating. Okay, so what is the heat addition in the combustion chamber? So the combustion chamber heat addition is the process 4 to 5. Okay, so basically the 4 prime to 5. Okay, so therefore QH is equals to what? CP T5 minus T4 prime. Okay, and one more is the reheating process. Reheating process is from 6 to 7. Okay, so putting all these values, 1.10 into 1500 minus 484.16 plus 1.10 into 1500 minus 1037.09. One six two 6.625. 1626.625 kilojoule per kg. Okay, net work done, W net is equals to WT minus WC. So WT is 1018.402 and WC is 405.14. So from here you will get 613.262 kilojoule per kg. Therefore eta is equals to W net divided by QH, 613.262 divided by 1626.625. So it's 37.70%. Okay. Clear? Fine. So let us go to the next question then. Consider a simple gas turbine, that is Brayton cycle, and a gas turbine with perfect regeneration. In both the cycle, the pressure ratio is 6 and the ratio of specific heats of the working medium is 1.4. The ratio of minimum to maximum temperature is 0.3 in the regenerative cycle, and the ratio of the, what is the ratio of the thermal efficiency of the simple cycle to thermal efficiency of the regenerative cycle. Now we already know that the thermal efficiency of a simple ideal Brayton cycle is 1 minus 1 by Rp to the power gamma minus 1 by gamma. Now we have to calculate. First we will derive an expression for, first we will derive an expression for efficiency of an ideal regenerative Brayton cycle. Okay. Fine. Now how will we do that? So before that, let us first check what is basically a regenerative cycle. Okay, so what happens if you look at the TS diagram of a simple Breton cycle? Okay, so what happens? The temperature at the exhaust gases of the temperature at the exit of the turbine is usually greater than the exit of the compressor, or in other words, T4 is usually greater than T3. So that means this whatever amount is greater, if we can supply this amount of heat, okay, if you can supply this amount of heat to the output gases at the compressor, then what you can do, you can reduce the heat required. Okay, so that means now if the heat energy, now if this extra heat energy at the exit of the turbine can be used to heat the exit gases of the compressor, then we can reduce the heat required in the cycle. That means if we heat required in the cycle, that means if we can reduce this, then what we can do, we can do this one. Okay, so for that, what we do basically, let me draw this one again. One, two, three, and then four. Okay, okay, so these two are the point X and Y. Okay, so that means now the heat input is basically this one. This one is basically a Q heat. Okay, and this is what your heat saved. Okay, this is the heat that is you are saving. Okay, so actual heat input is now from X to 3. It's not from 2 to 3. The heat input is now from X to 3. Note Q1 is equal to now Cp Tx, sorry, T3 minus Tx instead of Cp T3 minus T2. Okay, so that means instead of Cp T3 minus T2, now we are doing this for T3 minus T2. Now in ideal regenerative case, what happens? For ideal regenerative case, what happens actually for ideal regenerative case, Tx will be equal to T4 and T2 will be equal to Ty. Okay, so that means the total extra amount of heat is getting converted to heating up that one that is coming from the exit of the compressor. Okay, so now what will be my efficiency then? Eta regenerative, that will be 1 minus Q2 divided by Q1. Yes or no? So now my Q2 is also getting changed. Q2 is also equal to Cp times now Ty minus T1. Yes or no? So what I can write this one is 1 minus Hy minus H1 divided by H3 minus Hx. Yes or no? So that means this is equal to what? 1 minus Ty minus T1 divided by T3 minus Tx. Okay. Now for this case, once again I can put this expressions. Ty is nothing but T4 and Tx is nothing but, sorry, Tx is equals to T4 and Ty is equals to T2. So this one I can write as T2 and this one I can write as T4. Yes or no? Fine. So eta regenerative 1 minus, if I take T1 common here, what will I get? This one T2 by T1 minus 1. Yes or no? And if I take T3 out from here, I will get this as 1 minus T4 by T3. Okay. Now T2 by T1 is equals to what? P2 by P1 to the power gamma minus 1 divided by gamma, and T4 by T3 is equal to P4 by P3 to the power gamma minus 1 divided by gamma, and what is P4 is nothing but P1 and P3 is nothing but P2, so P1 by P2 to the power gamma minus 1 divided by gamma. Yes or no? So then what I can write this one as eta regenerative is equal to 1 minus T1 will be P2 by P1 to the power gamma minus 1 divided by gamma minus 1, and T3 into 1 minus 1 by P2 by P1 to the power gamma minus 1 divided by gamma. Clear? Now if you take the LCM here and if you do the calculation here, what you will get? Basically 1 minus T1 by T3 into P2 by P1 to the power gamma minus 1 divided by gamma. So that means eta regenerative formula is what? 1 minus T1 by T3 into Rp to the power gamma minus 1 divided by gamma. So this is the regenerative formula, and we already know the eta Breton formula, that is equals to what? 1 minus 1 by Rp to the power gamma minus 1 divided by gamma. Okay. Now what is given to us? Perfect regeneration. So in both the cycles the pressure ratio is 6 and the ratio of the specific heat is 1.4. Okay. So given Rp is equals to 6, gamma is equals to 1.4. Okay. Gamma is equals to 1.4. Ratio of the minimum to maximum temperature, that means T1 by T3 is given to you as 0.3. Okay. What is the ratio of thermal efficiency of the simple cycle? Therefore ratio of thermal efficiency of simple Breton cycle to regenerative Breton cycle is equals to what? 1 minus 1 by rp to the power gamma minus 1 by gamma, and this is for regenerative is what? 1 minus T1 by T3 into rp to the power gamma minus 1 divided by gamma. Okay, what is rp? 6 to the power 0.3, sorry, 0.4 by 1.4, so that is 0.40066, and this is 1 minus, sorry, 0.3 into 6 to the power 0.4 by 1.4, 1 minus 0.49944, okay, so 0.40066 by 0.49944, 0.8022. Okay, so since the ratio is less than 1, that means what? Therefore eta regenerative is greater than eta Breton. Okay, so simple regenerative cycle, sorry, simple Breton cycle has a lesser efficiency than regenerative cycles. Clear? Next is an ideal Breton cycle has a net work output of 150 kilojoule per kg, back work ratio of 0.4, and if both the turbine and the compressor had an isentropic efficiency of 85%, what is the net work output of the cycle? Okay, so what it is given to us, W net is equals to 150 kilojoule per kg. Okay, back work ratio, that is what? WC divided by WT is equal to 0.4, eta turbine is equal to eta compressor is equals to 0.85. So we have to calculate, so okay, we have to calculate under this condition what is the net work output. See, this net work output is already given to us, and this is when your nothing efficiency is given. Okay, so under this condition we have to calculate what is the net work output. So from here, first we will calculate WT and WC. Okay, so W net is equals to WT minus WC, and that is equals to 150. Okay, that is given. Again, WC divided by WT is equals to 0.4. This means what? WC is equals to 0.4 times WT. So therefore WT minus 0.4 times WT is equals to 150. So that means WT is 150 divided by 0.6 kilojoule per kg. Okay, so this one you will get 250 kilojoule per kg. Okay, so therefore WC is what? 0.4 times WT, 0.4 into 250 kilojoule per kg. Okay, so that is 100 kilojoule per kg. Now Next is when eta c and eta t are given, then wt prime is equals to what? Eta t into wt. Okay, that is 0.85 into 250 kilojoule per kg. Okay, we'll calculate it later on. Wc prime is nothing but eta c into wc, that is 0.85 into 100 kilojoule per kg. Therefore net work done is equal to what? Wt prime minus Wc prime, that is 0.85 into 250 minus 100 kilojoule per kg. Okay, 127. I'm sorry, this is a bit so the compression is a bit trickier one. Zero 0.85 into 250 212.5 kilojoule per kg. Now eta compression is equals to what? Actual work done of compression okay. So from here Wc prime is Wc divided by eta c. So what is Wc? 100 divided by 0.85 kilojoule per kg. 117.65 kilojoule per kg. So therefore net work done Wt prime minus Wc prime. Okay, $94.85 kilojoule per kg. Okay, fine. So then let us go to the last question then. A gas turbine power plant operating on an ideal Brayton cycle has a pressure ratio of 8. The gas temperature is 300 Kelvin at the compression inlet and 1300 Kelvin at the turbine inlet. Utilizing air standard assumptions, determine gas temperature at the exit of the turbine and decompression. Okay, so let me write the TS diagram. Okay, so P2 by P1 is given to US 8. Okay, and that is also equal to P3 by P4. Okay, gas temperature at the compressor inlet T1 is 300 Kelvin and turbine inlet, that is T3, is 1300 Kelvin. Gas temperature at the exit of turbine and compressor. Okay, so T2 divided by T1 is equals to Rp to the power gamma minus 1 divided by gamma. So T2 is equals to T1 into Rp to the power gamma minus 1 divided by gamma. So T1 is 300, Rp is 8, 0.4 by 1.4. 543.43 Kelvin. Okay, again T3 by T4 is equals to Rp to the power gamma minus 1 by gamma. So from here T4 is equals to T3 divided by Rp to the power gamma minus 1 by gamma. So T3 is what, 1300, Rp is what, 8 to the power 0.4 by 1.4. Okay, 717.65 Kelvin. Okay, next is what, back work ratio. That is WC divided by WT. What is WC? M Cp T2 minus T1, and this is M Cp T3 minus T4. T2 543.43 minus 300, 1300 minus 717.65. 0.418. Okay, next is what, thermal efficiency. Eta is equals to 1 minus 1 by Rp to the power gamma minus 1 divided by gamma. So that will be 1 minus 1 by Rp is what, 8 to the power 0.4 by 1.4. 44.79%. Okay, so with this I conclude today's class. Hope you all enjoyed. Thank you very much.